This is lecture number 9 for peer-to-peer MOOC, and we will be this time looking for a pastry routing example. So that's our objective in this one. So pastry was, as we know, which I have covered in the previous lecture, pastry was essentially derived from chord. So one important thing which they did was they first time actually went to a fixed logarithmic partitioning. So based on the digits which are there, fixed logarithmic partitioning was the one which was introduced. Okay, and then of course each node first of all looks into the routing table, which is based on this fixed logarithmic partitioning, and based on that decides to which is the next hop to which the query has to move. So the rule was that if you can get a better match, so with the current node ID, whatever is your hash which you are searching for some hash ID, the root of this. So you try to look at the match number of digits which are matching with the current node. So the rule is that if you are actually going to find out longer match, then you will hand over the query to that person. Okay. So in this routing table, and routing table typically will look something like this, which we had already discussed, that you will have only one digit with the current node, with only one digit which is matching. No digit is matching, you will be maintaining entries in that fashion, and when the one digit is matching with the current node, all those entries will be in the first row, two digits matching will be in the second row, and in the last one, n minus 1, if there are n digits, n minus 1 digits will be matching, and the remaining nodes will be entered here. So every time you match the hash ID and go for a longer and longer match. So with this example today actually will be showing that. And of course, if you don't get a longer match, even if the same match is there, the numerical closeness is looked into this, and you always pass on to the entry your hash ID or the query to a node which is numerically more closer to hash ID. Once you cannot do so, the routing actually essentially then moves on to use of leaf sets. So leaf, because all the nodes are actually assumed to be organized in a circular fashion. So leaf set is the numerically closest L by 2 nodes which are higher and L by 2 nodes which are lower. Okay. So these nodes are essentially being used once you cannot no more do the routing with the routing table. You will use this and find out your hash ID is closer to which node. So if it is closer to this node, you are going to pick this up. If it is closer to this node, you are going to pick this up. If it is at equal distance from both, you will pick up the entry which is numerically higher in this cyclic fashion. So essentially the layout, the circular arrangement is the same as what is used in the chord. So let's now move to the example. This was basically the principle which is used. So for keeping the example simple, we are going to consider a 4-digit node ID. And each digit will be 4 array digit. Okay, so the number which can be used is 0, 1, 2 or 3 only. So it's a modulo 4 numbering which will be used for each digit, which implies that you will have 4 raised to power 4, which basically means 256 node IDs are only possible in this whole space, and we have to use that. And the way I will give this whole example is that one node will be introduced at a time to the system, and one node I will be assuming as a bootstrap node. So for our case, bootstrap node number, I will mention that it will be 0, 2, 3, 1. So these are 4 digits, and no digit can be more than 3. It has to be either 0, 1, 2 or 3. Okay. And this bootstrap node is fixed. So normally in any peer-to-peer system, you will have bootstrap nodes. And these bootstrap nodes are used by any node to enter into the system. Now we also have to define that what will be the leaf set size. So leaf set technically can be of any size greater than 2, or similarly we also have to define the neighbor table, because we are going to use the proximity metric for doing a more efficient routing. So in our case, for this example, I am taking both of them to be 4. So normally it is whatever is a base value which you are using for digits, so that particular number is chosen, or twice of that is chosen. So that's normally the practice, but it can be anything. So even if with leaf set of 2, it is okay. It's always going to work. So as we have been actually seen in the chord, because you are actually pointing to somewhere. So if the leaf sets are there with the node, so you can always move towards a more optimal thing. So that actually advantage is there. In this case, because when we actually are doing routing with this, we are just becoming closer and closer to the hash ID, but after some point when you cannot find anything further closer, you have to decide on the root node on the basis of leaf set only. So leaf set is important, it has to be maintained, and L has to be at least equal to 2. So L always has to be greater than or equal to 2. And neighbor table, the larger we get, the better it is. So in our case I am taking just 4, but it need not be 4. So why we are keeping these neighbor tables is because when I have an options of actually putting more than one entry at this place, or maybe for that matter any other entry in the routing table, if there are more options are there, I will choose the option which is going to be closer to me in some physical sense. It can be RTT, round trip time, it can be hops, or it can be geographical coordinates, maybe long or longitude and latitude. So based on that I can find out the physical distance over the globe and then actually choose the ones which are closer to me. The idea is that whenever you are forwarding, you forward the message to, or the query or responses to the node which are geographically closer to you. While in case of a chord, this is not your choice, because your routing table is basically you just find out the diametrically opposite one, and whichever is the closest guy, that becomes the finger table entry. There is no choice, there is only one choice which is left, which you just keep on optimizing. Here you have actually more than one choice in the routing table, so therefore you become more efficient in using the internet resources. You actually tend to cover less kilometers, or you tend to consume less time for ensuring that query goes to the root node. And of course what we will do is I will just show you in the beginning that how the routing table entry moves, actually gets created as the nodes get added, and at some point I will assume some nodes and will create a stable routing table, and based on that routing table then I will simply add one and see what is going to happen, and we will assume a steady state routing table. But truly speaking, routing tables have to be in steady state when a node joins or leaves is not required. It can be done at any point of time. Routing table will always move towards the steady state situation, or it tend to the proper position where it should converge. So first node, as I told, will be 0, 2, 3, 1. Okay, and there is no other entry, so routing table of this will simply look, it will be, because we are having 4 digits and each digit can only take 4 values, so because the 4 values can be taken, so there will be 4 columns basically deciding that it will be corresponding to 0, 1, 2 and 3, and this one is for each digit. So in the first row, as we know that for 0, 2, 3, 1, so there no matching is required, so all entries which does not match with this, so entry which is going to start with 0 can match with this, so I will put this thing directly here. So I am going to put this thing with red color, 0, 2, 3, 1. So there is no entry available here, there is no entry available here, there is no entry available here. And then of course I will put the remaining 4 rows similarly. So it's, when I will start here, 0 is fixed, I have to look for all the entries with 0, 0. So the entries has to be 0, 0, x, x. But since there is no entry, this will be empty with this thing. Similarly, this will be 0, 1, x, x, it will be empty. 0, 2, x, x matches with itself, so I will put 0, 2, 3, 1 here. Again this entry will be empty. So continuing with this thing, I can actually very quickly write 0, 2, 3, 1, and then I can write 0, 2, 3, 1 here, and that's a routing table entry when only one node is existing. Now what we do is we introduce another node. So second node which we introduce is 2033. So let's introduce 2033 is the next node. So what will happen because of this? 2033 has to connect to somebody. It has to find out some node. Since this is the first node, I am going to assume it to be the bootstrap node. I call it a bootstrap node. So bootstrap nodes are the special nodes which are maintained in the system so that any new node who joins in can essentially enter into the system and then can update or optimize its own routing table entry or leaf set as well as the neighbor tables. So 2033 comes in, and 2033 is now going to ask for, will communicate to 0231. So it will come to know of, it will become aware of 0231. It will ask for, give me the, what is going to be my root node. So root node need to be searched here. So in this case 0231 doesn't have only this entry, so the first column only it can pass on, which can be used by 2033. Okay, second column will only be useful if the first digit is going to match with 0231. Okay, and 0231 will tend to now push this query or the search for the root node of 0231 towards the, depending on what entry it finds out. So once 0231 searches for 2033, it does not find any match. The only closest match is now 0231. So that's the root node. So only first entry will be used by him. So 2033 will actually populate its routing table based on the first entry which is present, the first row basically of which is being received. So first row contains 0231, which goes as it is. And the second entry is not available. There is no node with 1, starting with 1. So third entry will be 2033, which is itself, it will fill up on its own. Fourth entry is not there. Now the remaining entry has to be done by 2033 because all nodes here has to start with 2. So there is only one node. So 2033 will be coming here. It's actually because this is 0. Then 2033 will be coming here because this digit is 3. And this will be again 2033 because this digit is 3, and rest all entries will remain empty. That's a routing table after 2033 has entered into the system. 0231 will come to know of 2033, so it has to update this entry. So what it will do is it will now find out where it can place this entry. It can certainly place it here. It's not, the first digit itself is different. So it will end up in actually putting up this entry here, and you will have 2033. That will be the routing table after the first step. Now these also need to maintain their neighborhood tables. So this guy also has to have a neighborhood table which need to be populated. It also has to have a leaf set. In the beginning there is no entry, but once it comes to know of 2033, so that's the only entry which can be populated. So it will be 2033 here and 2033 here. Similarly, this guy will maintain a neighbor table and a leaf set. So leaf set will be 0231. Obviously, there is only bigger, and I can keep 4 entries, remember. And this entry will be now also 0231. Okay. So next node which we assume is 3210. So what will happen with 3210? So I am actually assuming 3210 is again actually talks to this bootstrapping node. And 0231 will request 0231 to find out who is the root node for 3210. Basically for leaf set population, that's what will be required. Okay, and of course along the process, as the node will keep on moving, they will keep on giving them the routing table entries being passed on to 3210. So if the first digit is not matching, the first row will be used. When the next guy, it will be forwarding it to the next guy. Next guy will send the routing table. If the first 2 digits are matching, if the first digit is matching, then in that case second row will be used. If first 2 are matching, the third row will be used, and so on. Okay, so in this case 0231 will send its routing table back to 3210. So 3210 will now populate its routing table. So the row will come. So 0231 can be directly populated. There is not an issue. So let me put it here. And of course 2033 will go as it is, the first row, but third row it can place itself, so it is going to do that. So 3210 it is going to do here, this will remain blank. Now the next row need to have first digit to be 3, so there is no other node, so this routing table does not give any other information for him, so it will just keep it vacant. It only has got the this routing table, not this one so far. Okay, so from this routing table these two entries are being populated by him. Okay, so now it will just maintain its own entry, so next entry has to be 3210, which will come here, 3210, because 2 will come in this row, 0, 1, 2 and 3. Okay, this is blank. Okay, next one will be 3210, so it will be 321, because of that it will come here, it is because of 2 you are here, and last one is 0, so it will be 3210 with the last digit. This is the new routing table for him. Now 0231 will now search for 3210 and try to find out the match. It does not have any match. Okay, so what it will do is it will essentially look for an entry. So there are only these two entries, there is no match, so it will find out if who is the closest numeric entry out of these, and will try to just pass on to that actually. So 0231 we can find out the closest numeric entry, how this will be computed. 0231 and 3210, we find out the difference. So if you arrange circularly, 0231 will come here, 2033 will come here, and 3210 has to be somewhere here. Okay, so this distance we need to find out, and we need to find out this distance. So if this distance is smaller, so this will be root node, if this is smaller, this will be the root node. So we compute it. Okay, so if I compute, so doing it actually I need to put in 1 here to compute the distance, because the modulo arithmetic. So 1 minus 1 0, 1 minus 0 0, 3 minus 1 is 2, 2 minus 2 is 0, and this essentially will become, so 4 minus 3 will be 1, so this is 1021. And if I will now compute with the 3210 to 2033 entry, I can do 3210 to 2033, compute this will become 7. No, this can't be 7, I am actually using a modulo 4 arithmetic. Okay, so I have to use the proper base value. So essentially it will be 4, because when you take the borrow 1, so 4 minus 3 is 1, this will be 0, 4 minus 3 is 1, so this will be 1, 1 minus 0 is 1, okay, 3 minus 2 is 1, so this is the entry. So which one is larger? So this one is certainly larger, this one is larger, so this actually means 0231, this is the root node for this. So this, its root node is going to be this guy. So the search will terminate, it will not be forwarded to 2033, so routing table will get stabilized here. Now what will happen to 0231? And of course I have to further mention about the route neighbor table and of course the leaf set. So 3210 will now build up a leaf set, and it will invariably will contain both these entries. Similarly for neighbor table it will contain, because all 4 is still not been there, so there is no choice, you have to keep all the entries. So these will be the entries for neighbor table and leaf set. 0231 will come to know of this guy, so it will also now maintain 3210 and 3210 at both the places, so they have populated. Now what will happen to this routing table? So 0231 will find out that 3210 does exist, so 3210 can be populated here. Okay, so it will simply create an entry 3210, nowhere else the entry is going to change. Okay, now at this point only 2 entries have updated. How come 2033 will know of it? In the next thing, the algorithm is that 3210 will now exchange the leaf set values with all the members which are there in the leaf set. So 3210 will send this whole 2 pairs to 0231 2033. 3210 also do the same thing with the neighbor tables, and it also request 0231 to send their neighbor table and 2033 also to send their neighbor table. Okay, or it sends the neighbor table to all these guys. It will keep on pulling and keep on sending. It will be done both ways. So for leaf set also the same thing. So you will retrieve the leaf set of these nodes as well as send its own leaf set to all both of these. Same will be done for routing table. So 2033 will become aware of 3210 because they will send the information 2033 which is there in leaf set as well as in neighbor table as in routing table. Okay, and of course 2033 will not give any new information to him, so there is no change. So once 2033 come to know of it, it will actually update the entries, and you will have at this point a new entry gets added which is going to be 3210. Okay, and of course you will also have, because of this update in the leaf set, 3210 will be happening. Update in neighbor table, 3210 will get added. Okay, and you have now updated routing tables. And now what we can do is we can actually add more nodes and build up a steady state table. Essentially, when these more nodes will keep on coming in the same process, the tables will keep on getting updated for everybody. So they will essentially will always come, if there is a bootstrap node will attach to this, ask to send the routing table back to them and ask them to find out the root node. So it will keep on finding out who is the best option, forward the query to that guy. That guy will also send the routing table information, leaf set and neighbor table information back to the new node. So they will keep on updating. And then there is a periodic neighbor table and leaf set and routing table exchanges which will be happening. So everybody will now make better and better entries. Now for doing neighbor table we need to know the topology, because we are now here doing it based on the number of hops. That's the physical distance which we are actually assuming. So let's see, we will actually first of all try the addition of a node, and then of course you will be also figure out that what happens if we are going to remove a node correspondingly. Okay, the procedure almost kind of remains same. So we are going to add the following nodes more. So 2210 we will be adding, 2033 was already present, 3320 is going to be added, 0001 will be added. So I am at over time these are the nodes which have come in. 1021 has come in, 3213, 1321, 1021. Yeah, 1021 has already been placed here, so it need not be shown put up again. Okay, so 2033 was already existing and 0231 was also already existing. So these are already existing nodes. In between we also had 3210 being added, so I need to put that 3210 also. Okay, so 3210 was already existing node which have been underlined. So we also need a topology as of now. So I am just taking some example topology, and we will be looking at hop distance. So I am writing the node IDs, and we are going to connect this and this 3213, and of course let's connect this will be 001. So that's a topology which we are considering, and with this topology, an important thing, the proximity metric, we are going to take it as not RTT or something, it's number of hops. Okay, when you have more nodes with the same number of hops, we will just choose whichever one is numerically closer, we can choose that, or we can choose the other way around. Okay, so normally the better is that if you are having A, B, C, D, so every time you choose a different value if you are choosing 4 numerically closer values. So this should be different as far as possible. If you don't have an option, keep this one as different as possible. So that way you have a diversity of choice in the proximity metric, because that becomes important when you are trying to fetch the routing tables or their leaf sets or their neighbor tables. So your routing table entries will always be optimal in terms of the proximity metric. It's for that purpose we have to do it that way. Now let's build up the routing tables for each one of them. Okay, how they will look like. So I am assuming under steady state condition, we will also have to write the leaf sets for each one of them. So let's do this. So the leaf set I am going to build up a 4 by 4. This is the routing table. We will also have a leaf set entries. We also have a neighbor table entries. All 4. Okay. So let's now create for the first one. And when the multiple possible entries are here, I will be always choosing the one which is closer in terms of the proximity metric. Okay. So let's choose for, we can start with any node, but we have to do for all 9. So let us start for 0, 2, 3, 1 first. So first entry will obviously will be 0, 2, 3, 1. Let me put it with a different color. Okay. And then of course we have to choose an entry which starts with 1. So you have only 2 entries, 1, 0, 2, 1 and 1, 3, 2, 1. So obviously it has to be 1, 0, 2, 1, which is 1 hop away. Other entry is 2 hops away actually. So this will not be kept. And then we have to have the entries with starting with 2. So there are only 2 entries, and 2, 2, 1, 0 obviously is the closer one. So we will be keeping that. Under steady state, that's the way they should converge actually. With 3 we have 3 possibilities. So 3, 2, 1, 0 obviously will be the choice in this case. The next entry has to start with 0, 0. So 0, 0 there is only one entry which is 0, 0, 0, 1. So I will retain that. We don't have any entry with 0, 1. So this is dash. 0, 2, 3, 1, this itself will repeat. 0, 3 there is no entry. Then we have 0, 2. 0, 2 there is no entry. This is itself. Okay, this will be 0, 2, 0. 0, 2, 0 there is no entry. 0, 2, 1 there is no entry. 0, 2, 2 there is no entry. 0, 2, 3, 1 is there. After that, in fact, there will be no entry except 1. So this one will be dash 0, 2, 3, 1 dash dash. This will be the routing table. The leaf set entry now, we can also put them in a circle and then see how they look like. Okay, so this is going to be say 0, 2, 3, 1. So next entry has to be starting with 1. So this will be 1, 0, 2, 1. Next entry will be 1, 3, 2, 1. Okay, after that we will be having entry with 2, so it will be 2, 0, 3, 3. Then you have 2, 2, 1, 0. All entries 2 are with exhausted. Now we will start with entries with 3. So it will be 3, 2, 1, 0, 3, 2, 1, 3, 3, 3, 2, 0, and after that it will be value again will come back to 0. So we have total 3 plus 3, 6 plus 9, total 9 entries on the ring. So that's a numerical relationship between them. So leaf set for 0, 2, 3, 1 we can actually compute from here. So and I need only 4, so these 2 and these 2 will be the leaf set for 0, 2, 3, 1. So I can write that. So I can write 1, 0, 2, 1 and 1, 3, 2, 1. That's a one side, and other side is going to be 0, 0, 0, 1 and 3, 3, 2, 0. So neighbor tables will come from here. 0, 2, 3, 1 actually has one neighbor is 2, 2, 1, 0. Obviously you have 1, 0, 2, 1. You have 3, 2, 1, 0. Okay, so there is no entry with 0, which is, so I have to just find out which one is closer. So 1, 2 and 3 has been done. So next entry either can be this, this or this. Okay, there is no other entry which is feasible, so I can keep any one of them. So I will try to keep entry with 0 if possible, but there is no entry with 0 possible, so I will keep any one of them. So I can keep say 3, 2, 1, 3. So that's a neighbor table actually, the 4 closest node for 0, 2, 3, 1. Similarly, I can now build up tables for others. So let's do it quickly actually. And So let's do it, and then this one will be for 0231 has been done. Then we can start with 2033, which was our second node, and very quickly writing it down. 2033 will be here, 2033 will be here. So I am filling up. I am not explaining how it is going to be done. Probably you understand it by now, but I have to just fill up the entries. So remember, from 2033 there are two entries which can go with 0, but both are 2 hops away, so I can pick up any one of them. So this is pretty fast, and of course leaf set you can actually figure out from here. 2033, so it will be and 1321 and 1021. So neighbor table you can again compute by looking at this table. So neighbor table, if you compute for 2033, so it will be 1021, obviously 3320. So remember, most of the entries from neighbor table, we are always trying to use it, or the whoever is are in the neighbor table of these members. So these members also have a neighbor table. So that's why it makes good sense to actually get the routing table from these guys and fill up those entries, because those will be more closer to you actually always. Okay, over time that's what you will figure out. So 2033 has got these two. Then it can pick up 2 hops away. There are this node and this node. Any one of them can be picked up. So 1 and 3 we have already picked up. Okay, so we would like to pick up a guy with 0. So 0 obviously should be there. In fact, it could have been this as well as this. Any one of them could have been picked up. I picked up in this case 0001, but and then of course one more entry which has to be done. So I can choose anybody arbitrarily, so 2210 maybe. Okay, so this is a neighbor table. So doing it this way, this is so other tables also can be done. So I am not doing them here. What I will do is I will actually now assume that routing tables are there, and I will try to add. So whenever it is required, I will compute that node's corresponding routing table. I need not, because all routing tables are not going to participate when I am trying to add a new node. So whichever will be required, we will just populate that and use that. So okay. So similarly, we have neighbor tables and then leaf sets. So we will also consider that. Okay. So this basically I am trying to give an example. So you can actually work out on your own and then verify this particular thing. So let's now add a new node. So new node which we are going to add is, let it be 2012. That's a new node which we are adding. 2012 is a new node which I want to add. Now what will happen? Now bootstrap node I have to decide. So as usual I am going to take the same bootstrap node which everybody else is taken when the network started, 0231, and with that now let's find out. So 0231 2012 will now talk to 0231 and ask him that try give me the who is going to be my root node. So Now let's we'll actually use the, I will just draw the routing table. You can verify whether it actually comes under steady state or not. So 2012 will first of all talk to 0231. As a consequence, because the 2012 has first digit as 2, this one is 0, so first row can be directly used by 2012. So let me build up a routing table for 2012. So you do it. So 2012 will use directly this routing table as it is, except wherever this entry is there, it will put itself, because this has to be closest to itself using proximity metric. So you will end up in getting a 0231 here. Okay, so I will now put it with a different color, 0231 1021, because it does not know anybody else. So there is no question of optimization. Okay, so it does not even have its own leaf set. So it's as 1021. So that's where the entry will change. Now it will be 2012. A change is going to happen here, and then you will have 3210. The second entry it can't keep because they all have to start with 2. So I can't use these entries of 0231. Okay. So now 0231 will look for 2012. 2012 will come into its knowledge. So it has to update its routing table if it is required. So it will look into the, it can only happen 2210 can be replaced by 2012. Okay. And the way we are adding this entry, so I am actually keeping this entry is at this position. I am keeping this entry here, 2012. Okay. So 2012 is far off compared to 0231. So it won't be preferring that, and it will maintain 2210, which is one hop away. Okay. So there is no change in the routing table of this, no change in the neighbor table, and of course, will there be any change in leaf set? Yes. Let's see if there is going to be any change in leaf set. The 2012 will be getting inserted here. Okay, this will get inserted here. So there is no change even in the leaf set. Leaf set actually remains same. Neighbor table remains the same, so there is no change in 0231. Okay, but using these neighbors, it will build up its own leaf set and neighbor table. So what it will be actually? So as of now, it is only aware of the nodes which are present here. Based on that, it will maintain its own leaf set, and whatever leaf set information which will be retrieved from 0231, it will use that. Okay, so using that, so if you look at 2012, it is aware of 2033. No, it is not aware of that. 2210, it is not aware of. It is actually becomes aware of that. So we will just actually use these entries. 2012, anything which starts with 2 had to come here. 2210 will be the one entry. So I am just increasing the entry 2210. There is, and then after that we have 3210. That's the leaf set, the higher side part. The lower side part, it will come to know of anything which is lower than 2, because there is nothing else with 2 actually. So 1 will be there. So only 1021, so it will just put 1021 here, and anything lower than that is 0, so it will be put 0231. So that will be the leaf set to begin with actually. Okay, when the next hop, the routing in search of root node, the packet will be forwarded. So that information when it will come, again this everything will get updated. Neighbor table will come actually from again the network which is there. It will do a kind of a test and find out the hop. So 2012 is in fact, ideally speaking, if it is not is the internet hops which we are talking about, and this is a internet hop connectivity. Okay, so it can actually send a router and find out. Later on it will find out this guy is also part of the DHT. It will use that, but it's a hop in the at the IP layer. So 2012 is going to be closer to whom? So we have to figure out that. So doing this, I will just slightly reduce the size of this so it becomes easier for me, and then I will come back to the same size. Yeah. So 2012, I am going to only look at these nodes. 001 is participating here, so it will become one of the entries, is one hop away. 3213, is it present here? No, it is not present anywhere, so that won't come. Now 3320, is it present there? No, it is not present. 1321 is not present. 3213 was not there. 3210 is there, so it will maintain 3210 as the next closest one. Okay. So these nodes are all exhausted, which are 2 hops away. So now 2033, is it present here? No, it is not present in any one of them as of now. Okay. So what will happen? So 2033 will not be coming, and 0231, it is present, so 0231 come. 1021. So this will become the neighbor table to begin with. Now this guy will search for 2012, the best match entry is 2210. So it will, this query will be of the root of 2012 will be handed over to 2210. So I need a routing table of 2210 now. So let's create that. So by looking at all the information, I can create that very quickly. I will only be creating what is required. Okay. So this is going to be 2210. So 2210 routing table will look like, the first entry has to be starting with the 0. So 2210 is here, so 0231 obviously. There is the closest guy. With 1, it is 1021. With 2, it is going to be 2033 obviously. And with of course 3, it will be 3210 obviously. Okay. With 20, if any entry is 2033 is there, so it will be maintaining 2033. Okay, then we have 21. If is there anybody else with 21? There is nobody else, so it is dash. With 2210, this will be itself. Now I have to make sure that this 2033 cannot be kept. This has to be replaced by 2210, because that's the closest node to itself. So this needs a correction. And of course the last entry will be 23. There is nobody, and there is nobody, I think, with anybody else. With sorry, this has to be changed slightly. Is at wrong place. Okay, 2022 will come here. Okay, this is 220, 221. This has to be here. Sorry. And this has to be 2210. So this will be the routing table for 2210. So when 2012 will come here, it will try to do the match, and the better match will be now 2033 and 2210. So this will be the better match which it will get in the second layer. So it will hand over to 2033. So this query will be now handed over to 2033. But this routing table information will be sent back. Okay. So the first entry it has already prepared. It will find out if there is a better option. which is get now 2012, which will keep it itself. Remaining entries are as it is, actually there is no new information. So from the second row it will find out this itself has to be there at 2012. Okay, so second entry will be dash, there is no other node, no new information it can get from anybody actually. Okay, so this one will be now 2210, this will be dash 2012 dash, there is nobody else with 2, there is only 2210 2033. Okay, so 2012 2033 will come here. Okay, and of course the last entry will be 2012. With 201 there is no other nodes. With 2033 will come, so there is one more entry which will get populated. Okay, so which knowledge will come from here, and that will be used in this case. This is a better match. Okay, so we have got this updated, and once you have got knowledge of these particular nodes, so again these leaf sets and neighbor tables have to be updated. Of course this 2210 will also tell about its leaf set and neighbor tables, so that information also has to be used. So 2210 stands here, it is going to contain 3210, 3213, and of course 2033 and 1321, and neighbor table again it will compute from here, so it will consist of 1021, 0231, and of course you can put 2033 and 3210. So there are two guys, two hops away, and one person, which is two persons which are one hops away. So once all this information comes, there are a lot of information which is based on that the optimization has to happen here. So now you have more knowledge. Almost all nodes are actually, so 2012 now is aware of these nodes, it's aware of these nodes. Because of 0231 it has already become, so it has become aware of everybody almost. So by this time then it will essentially now do the hop count and will optimize itself to find out the best leaf set. So everything will now be essentially merged together, because all information is there. This is all organized, so it will find out its own leaf set, and leaf set will get corrected. So leaf set will now no more contain this information. So leaf set will change to, because more information is coming. So this will become now 2033 and 2210, and on the other side it will be 1321 and 1021. So that will be the leaf set. So neighbor table similarly will get updated now. So it's basically by physical measurement it will be coming out to be 0001, 3213. So earlier these two guys actually were being picked up because there was no knowledge of the intermediate guys, other guys. So we can now put 3320 and any one of them, so it can be 1321. So this will be the new routing table, and these guys will also get updated, so they also need to update. So for example 2210 will come to know of this thing, so it will update its leaf set. So 1321 will be gone and you will have 2210 now coming in. Okay, similarly the neighbor table will also get updated. For 2210 of course it won't be making a difference, but this change will happen at all the nodes consequently. And that's how the routing tables will keep on updating and keep on remaining in optimal position. So whenever you want to do a essentially routing you have for any hash ID, you will just essentially be picking up, so wherever at whichever node you are, you will be first of all looking at routing table, finding out the longer match, or even same match, then it has to be numerically closer. Now similarly when you delete, the entries will essentially be purged. So some entries from For example, if you actually have two nodes which are the leaf sets in front and two in the back, you are here. So if this guy dies off, so you are actually seeking the leaf set from each one of them. So all leaf sets are coming to you. So this guy will be telling who is there in next two. So the moment you figure out this guy is not there, you will now get this particular set, you get this set, you get this particular set, and based on that you will make a choice. So this entry will be purged, and this you will now make the entry to these four guys. So this entry will get updated actually. The same thing happens with neighbor table continuously. So any better option you come, you keep on updating. So with deletion also this will automatically repair, but this is a very fast mechanism. So this was the example for pastry routing. So next we will be looking at the Cadmilia routing, which is another one, and which works in slightly different way, because here the distances are being computed in this fashion. We actually don't worry about the numerical distances. So far I can find out a way that you start at any node and you can be routed, and you will always reach to a unique node. So given the hash ID, there is a unique mapping to a node which we call the root of the hash ID. So far this can be done. The system can actually be used for DHT based network. So with that we close, and see you in the next lecture.